So before I present the new material, let me explain our current situation. So where we are at this point. Yeah. We just complete the brute force method, right? The previous slide, the direct, straightforward multiplication, addition operations, so we can find the value of the polynomial. Yeah. So now, before we do the improvement, our goal, we want to find a more efficient algorithm. Before we do that, we want to measure the performance of the current method. So here you can see, at this point, so what we are doing now, I need to let you know what we are doing now. All right. So because we need to do a lot of things to solve this problem. So let me just, what we are doing now, we need to measure the performance. That's, we are doing now. What we are, so we are doing. Measure the performance. All right. And we can see our algorithm, basically what we are doing in this algorithm, additions and multiplications. These two types of operations. All right. And here, the question, do we still have room to manipulate addition and multiplications? Regarding the improvement, you need to change something, right? So you cannot use the old way doing additions, multiplications. If you use the same way, you won't get improvement, right? So here, this question means we need to do something different in order to get an improved algorithm. So the question, do we still have any room to manipulate additions and multiplications? So we need to find a different way to manipulate the additions and the multiplications. At this point, we may not know that, right? At this point, we may not know that. All right. So next, so the difference we want to make. So here we want to change something. The difference we want to make is we want to change the order of the operations. Orders of these two types of operations, additions, multiplications. We want to change that. Okay? So that's the direction we want to go. How to change? At this point, we don't know how to change. All right. So do we have other orders to apply the operations? We do not know at this point. So that's the next problem we want to solve. All right. Then, so when we get back to the measure, get back to the measure, to measure the performance, then this question, targeting this question, measure, how to measure the performance. Can we use the execution time to measure the performance? Because we want to know how fast this algorithm runs direct, direct way of thinking is we just use the execution time to see how fast it runs, right? Yeah. So here, actually, for this question, there is a problem. If we use the execution time directly, although we get an objective measure, not subjective, it's objective, because we have a specific number for the time, but it's unstable. If we use this way to measure the performance, it is unstable. So what do you mean unstable? Unstable, it means because nobody knows what computer you are using, right? So different people, they run this algorithm on different computers, right? Some computers running faster, some computers are slower. Some people may use the supercomputer, some people may just use low-end computers, right? So if we use the execution time, we do not treat it as a good, stable measure for the performance. So we like to choose some performance measure that does not rely on the hardwares our users use. So supercomputer or low-end computers, there is no difference. That's the stable measure we want to have here. Okay, all right. But the question, how do you get a stable measure here? All right. So here, hardware part. Actually, there is another possibility for the software part. It's also unstable, the execution time. Software part, because different programmers, they implement the same algorithms in different ways, right? So when programmers, when they write the implementation of the same algorithm, experienced programmers, they can write the code very efficient. But for those programmers without much experience, so they may not do the implementation efficiently. So in that way, there is also difference, significant difference between different implementations. So still not stable. So we want to choose some stable measure that does not rely on hardware and the software conditions. So, all right. So our goal, no matter your hardware selections or software implementation details, we should have the same measure number for the performance or efficiency. Same number used. Nothing to do with hardware software conditions. Okay? How to measure efficiency? So not very hard. So although it looks like we want some perfect measure, but there is some simple way to get it. So what's that? So here, using number of additions and multiplications. That number of additions, number of multiplications, those two numbers, if we use those two numbers to measure the efficiency, then you can see it does not rely on the hardware, right? A supercomputer, low-end computers, same number. You use the same number of additions, same number of multiplications for the same algorithm. Similarly, for coding, for programming implementation, same number of additions, same number of multiplications. So it's a stable measure if we use the number of operations. Yeah. All right. But there is another problem. Yeah. After we solve the first problem, another one. Yeah. Because here we have two different types of operations, additions and multiplications. And we know the execution times used for addition and the multiplication are different. Yeah. When we do an addition and a multiplication on the same computer, the execution times are different. Yeah. Addition is much faster than multiplication on the same computer. So this time we need to consider this factor, the difference between addition and multiplication execution time. Yeah. All right. How to solve that problem? Yeah. Otherwise, we cannot get a fair measure, right? It's hard to get a fair measure for the overall efficiency. Yeah. So the solution to fix it, we add some reasonable assumptions here. Reasonable assumptions. Yeah. All right. Here, in order to bridge the gap between addition and multiplication, the difference on their execution times, we make some reasonable assumption based on the real world situation. Yeah. So what's that? Yeah. So we assume each addition takes 1 unit of time. 1 unit of time. Yeah. So here we do not specify how large is that unit. How large is that unit? Yeah. Yeah. But I can give you some idea, a rough estimate of this unit of time. That's approximately around certain number of nanoseconds, ns, nanosecond. Do you know how large it is? 1 nanosecond. How large is 1 nanosecond? Do you have any idea? Yeah. So 1 millisecond, 1 microsecond, and 1 nanosecond. Yeah. That's small. Yeah. Yeah. So here, let me just write 1 nanosecond. 1 ns equals 10 to the negative 9th of 1 second. Yeah. Or 1 billionth of 1 second. So that's 1 nanosecond. Okay. Yeah. All right. So yeah. So on a modern computer, in a CPU, yeah, it takes, probably between 1 and 2 nanoseconds. So doing one addition, yeah, it takes the time usually between 1 and 2 nanoseconds. Yeah. All right. So then for the multiplication, it takes 10 units of time. 10 times, approximately, yeah, not exactly, but approximately 10 units of time. Yeah. For simplicity, here let's assume 10 units of time. Because if we make this assumption, we do not alter the original problem significantly, right? Yeah. So we change slightly, but the problem still has the same difficulty as the original version, right? Yeah. So no significant change here. Yeah. But in our discussion, it's much easier to, do the analysis work with this new assumption. Yeah. All right. Now we are ready. So here you can see what we are doing here, preparation work. Yeah. In order to make our discussion smoother, so we do this much preparation work. Yeah. All right, so let's do the next step, B.2, estimate the cost. Now we are ready to estimate computation cost to evaluate a polynomial using the brute force method. Yeah. So here we want to see how well the brute force method can perform. Yeah. Yeah. All right. So yeah. To do that, now we need to do the detail estimate. Yeah. First, let's look at the first subproblem. We split the original problem into here two subproblems. The first one, we count the number of additions. Second subproblem, we count the number of multiplications. Yeah. So then we, put them together to get the overall efficiency measure number for the brute force method. Yeah. All right. So the first subproblem. Yeah. Count the number of additions. Yeah. Now I ask you to look at the formula here. Yeah. This polynomial formula. Yeah. So you can see many plus signs, right? So each plus sign represents one addition. So now my question is, can you tell me how many additions do we need to find the value of this polynomial? Here you can ignore the multiplications. You only look at the number of additions. Can anyone tell me the answer? How many? So you just type on the chat area so I can see your response. Anyone? You can see how many additions can you see? Yeah, just estimate, or you can guess. Okay, you can guess. Yeah, just some number. Yeah, try it. Anyone want to try? Yeah. Look at the formula. Yeah. Look at the formula. How many plus signs can you estimate, yeah, or guess, yeah, related to that n? Yeah. So here we call degree of this polynomial is n. So the number of addition, yeah, so here maybe n additions plus, yeah, all right, good, yeah, so yeah, I see a response. Yeah. All right, so first, okay, first I want to say your answer is correct. Yeah. Your answer is correct. The answer is n additions. N. Yeah, that's simple. That's simple. N additions. Yeah. Plus a sub 0. Yeah. Yeah. Even that plus a sub 0. Yeah. Yeah. All right. So, yeah. So here, the question, yeah, how to see that n is correct or not? Yeah. So here, let me just do some work to convince you this n number is correct. All right. So here, I like to introduce some problem-solving skill here. Yeah. So the strategy, the strategy here, problem-solving strategy. So this strategy work on the easier part first. Easier part first. Actually, so here I go back a little bit. Because here we have two tasks we want to solve. The first task, we need to count number of additions. Second task, we count number of multiplications. So when we have two tasks, we want to solve the first one. Because first one easier. Counting number of additions much easier than counting the number of multiplications. All right, so that's the simple strategy. Second, right. So here, when we count the number of additions, the hard part is this: how do we handle the ... Because we skip many terms, right? So when we write the formula, we cannot list all the terms. For any given degree number n, we cannot list all the numbers, right? So we have to skip most of the terms using this ... notation. But the problem is, if we skip so many terms, how do we keep track of the terms? It's hard to keep track of the terms, right? We get lost. So that's probably most of you, when I ask you the question, how many additions, most of you do not feel confident to give me an answer, right? Most of you do not feel confident because so you do not know how to handle this ... part. All right, so here I want to introduce a counting technique to help you keep track of the missing data. All right, so here we want to find an effective way to keep track of the invisible terms. What's that? This counting technique is called counting by reference. Counting by reference. Okay? All right. Because all these plus signs, it's hard to identify all those plus signs, right? How do you identify all the plus signs? Okay? So you see the first few, last few, and how to identify those missing plus signs in the middle. It's hard to do that, right? So in order to identify those missing plus signs in the middle, we choose appropriate reference objects. Reference objects. So here, let me explain this method. Very simple. All right. So the essence of this method, we want to discover one-to-one correspondence between two mathematical objects. Two mathematical objects. One-to-one correspondence. So then we can find the answer in an indirect way. Not direct way, indirect way. We can find the answer. Let me use this diagram to explain this idea. Suppose we have two different mathematical objects, object 1 and object 2. If we can establish some one-to-one correspondence between these two objects, if we can do that, so later I will show you how to do this one-to-one correspondence between two mathematical objects in this polynomial. For object 1, it's hard to count. Object 1 is hard to count. Here, object 1 plus sign. Yeah. We treat plus sign as object 1. And we can see it's hard to count directly how many plus signs. The number of plus signs, it's not easy to count directly. All right? Yeah. But object 2, easier to count. Yeah. They have the one-to-one correspondence, and the object 2 easier count. Then this new method, this counting technique, counting by reference. So we use object 2 as the reference to object 1. So we just count the number of object 2 instead of counting number of object 1. So when we get the answer for the number of object 2, we use that same number as the number of object 1. Because this one-to-one correspondence allows us to use the same number as the counting result. All right? Yeah. So here it's a little abstract. Yeah. So let me use this polynomial, the concrete example, to show you this idea. Yeah. Object 1, a plus sign. Each plus sign is an object of object 1. Yeah. Object 2, a subscript. Yes. So what's the object? So for the first plus sign, this is the first plus sign, we associate it with the first subscript of the coefficient at its right hand side. Yeah. Yeah. A1. Yeah. Not A0. Yeah. Yeah. If A1. Yeah. The subscript of the coefficient A sub 1. Yeah. The second plus sign we associate with here A2 x squared. So 2. Yeah. The last plus sign, so here, so the last plus sign we associate with the subscript of its nearest right coefficient subscript, n. The n. Now you can see we get a one-to-one correspondence, right? Yeah. Yeah. So each plus sign, so the first plus sign corresponds to the subscript 1. Second plus sign corresponds to the subscript 2, The last one corresponds to the subscript n. And the sequence of plus signs cover these consecutive integers from 1 through n, consecutive integers. But counting plus sign directly, it's relatively hard, but counting the number of subscripts much easier, right? Now counting the column of all these consecutive integers 1 through n, it's trivial. So we get the answer n. We get the answer n. Yeah. So in that way you can see, yeah, that's the reason the answer is n. Yeah. So here I hope with this simple example, so you can get an idea of this counting technique. This counting technique, counting by reference. Yeah. But you need to choose appropriate reference objects. Okay? Yeah. All right. Yeah. So, right. And here, when we do this one-to-one correspondence, we can ignore the first term. Yeah. The first term. Yeah. So, yeah. All right. Yeah. All right. Yeah. So, all right. So we finished our first task, first subproblem. Next, second subproblem. count the number of multiplications. Number of multiplications. Yeah. All right. So this time, yeah, let's do the counting work. Yeah. We know for each term, based on our discussion in Monday's class, we know there are k multiplications for this typical term. Yeah. All right. Now we want to accumulate the number of multiplications from all the terms in this polynomial. Yeah. All right. Yeah. So there are n plus 1 terms. Yeah. So if you look at the subscripts, there are n plus 1. Yeah, because the subscripts running from 0 through n. So that's why there are n plus 1 terms. Yeah. But the first term, a0, in the first term, a0, there is no multiplication, right? So the first term does not contribute any multiplication. Yeah. So we can skip it. We skip the first term. Yeah. So let me do a chart here. Yeah. So I list all the n terms with certain multiplication contributions in this chart. Okay. All right. So 1, 2, 3. Yeah. So consecutive integers. 1, 2, 3 till n. The last term, n multiplications. Yeah. So let's add them up. Yeah. The summation of the first consecutive positive integers, there is a formula, right? There is a famous formula. Yeah. So here I do not ask you, so I just write it out. So it is 1/2 times n plus 1. Yeah. So remember the last time we learned the formula 1 square plus 2 square plus 3 square plus dot dot dot, right? Yeah, n square. Yeah. Yeah. Here, this summation much easier than this square version. Yeah, let me just recall from last one. 1/6 n plus 1, 2n plus 1. Yeah. So that's the formula we learned last time. Yeah. All right. So here, no square. Yeah. Just you know, consecutive numbers directly. Yeah. All right. Yeah. Let me see. Yeah. Something. Something. What's that? All right. Yeah. Anyway. Yeah. All right. Yeah. So then the answer, the total number of multiplications, 1/2 times n plus 1. Yeah. All right. Yeah. 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 So that's the answer. Yeah. Then next step, after we get the number of multiplications, we want to convert it to the total units of time. Yeah. Yeah. Remember our assumption in the previous slide, number of units. Yeah. Yeah. All right. Yeah. So, all right. So let me check. Let me check. All right. Yeah. Yeah. All right. Yeah. So we want to see these number of multiplications can be converted to how many units of time. How many units of time? Okay. All right. Yeah. Yeah. So here, Yeah, based on our assumption, yeah. So here, remember the problem? Yeah. So when I, do something here, yeah, my PowerPoint slides got freezed. Yeah. So if during my presentation, if I do some actions on my presentation computer, then the PowerPoint slides freezes. Yeah, so I cannot. So I have to get out, then get in again to enable the control. Yeah. So that's why I try to avoid doing any activity on my presentation computers. So I have another laptop to to view the messages, to do the actions. Yeah. All right. So now, yeah. So we are here. The total units of time. Yeah. So yeah, look at here. The summary. We already get this part. We need to use n units of time for the n additions. Now, how many units of time we need to use for the multiplications? Yeah. And we know, yeah, we just got this number, this many multiplications. But based on our assumption, each multiplication takes 10 units of time. 10 units of time. Okay? Yeah? So we need to multiply this number by 10. 10 times this number. Yeah. So after simplification, so that is 5n times n plus 1 units, time units. Yeah. All right? Yeah. So now let's put units from these two types of operations, addition, multiplications, together. So n plus 5n times n plus 1. So we get a total number of units, 5n squared plus 6n. Yeah. So can you see that? Yeah. So here, can you see the total number of units? And this is the measure. This number of units of time, this is our performance measure. Yeah. So we feel it is a fair measure. Yeah. It is fair measure. And this measure does not rely on hardware, software conditions, right? Yeah. So, yeah. Although we use assumption, that 10-to-1 ratio assumption, we use that. Yeah. All right? Yeah. So now we have the, progress. Yeah. So we get this performance measure here. Yeah. So let's go to the next step. Next step, we want to improve this algorithm. Yeah. Last time I showed you a simple example. Yeah. Remember last time I used the calculate x to the fourth, and we can use two multiplications to get an answer. Yeah. So recall what we did last time, multiplications. Yeah. So that means there is a hope to improve the brute force method, right? Yeah. So our next round of work, we want to improve this brute force method. Yeah. Yeah. But when we do the improvement, we want to reduce the total number of units of time used by the algorithm. by the new algorithm. We want to reduce this number to improve, for the improvement. Yeah. All right. So the question is how to improve it. How to improve it. Yeah. All right. How to reduce this number. Yeah. So our next step, we want to reduce the number. Yeah. Improvement strategy. Yeah. Here there are two parts, addition part, multiplication part, to be improved on. Yeah. So the question, which part we should spend our effort on? Should we spend our most effort on addition part or on multiplication part? Think about it. Okay? Addition part, multiplication part. Okay? Yeah. So which part gives us more room for the improvement? More room for the improvement. Yeah. All right. So remember, the addition part, the number of units for the addition part is n. The number of time units for the multiplication part is 5n squared plus 5n. Okay? So you can see the multiplication part much larger than addition part. Then can we say with this observation, yeah, and also other than the number, so first you see the number is so much, yeah, so yeah, all right, so here we already converted the time units. So here this is the units number. Yeah. The units number, we already used the unit cost for multiplication over unit cost for addition 10:1 ratio. We already used that information when we convert it to the units of time. Yeah. All right. So based on these two numbers, one much smaller than the other, which part do we have more room to improve? Right? So think about this question. These two parts, which one allows us to have bigger improvement room? Yeah. Yeah. So look, right, multiplication, definitely. Yeah. Eldon, yeah. So because based on your intuition, for the addition part, the most you can improve, you cannot reduce the time units more than n, right? At the most. So for the first part, the biggest reduction less than equal to n, right? You cannot do reduction more than n units. Yeah, because all the unit number for addition part, that's n. So you cannot do reduction more than that. But if you look at the multiplication part, you have much bigger room for the improvement. For example, can you do the reduction? So here I'm talking about this multiplication part. Can you do reduction, n squared reduction? Can you do n squared reduction? It's possible, right? So here, yeah, because we have 5n squared. We have at least 5n squared units. We just reduce the number of multiplications by 1/5. 1/5, approximately 1/5. Then we do n squared reduction. N squared reduction, that's already much more than the total number of additions in the first part, right? Think about that. Yeah. So here, based on this observation, our conclusion is we should put our effort on the multiplication reduction part, not addition reduction part. Okay, multiplication reduction. So our main focus is on the multiplication reduction. All right, yeah, conclusion. Focus more on multiplications. Yeah, all right. So here the strategy. We set the strategy from our next round processing work. Reduce the number of multiplications. Yeah. All right, so new question. How to reduce the multiplications? Yeah. How to do the reduction on the multiplications. So the topic B.3, Horner's rule. This Horner's rule tells us what is the best way to do the reduction on the multiplication part. Yeah. All right, so let me show you the main idea of the Horner's rule, yeah, the strategy. Yeah. Here, to get an idea how to do the reduction on the multiplication part, let's use this strategy. Study a simpler case. Study a simpler case. Remember, we used this strategy last time in our Monday's class. So do simple experiments. Remember? Yeah. So when we work on simpler cases, actually we are doing experiments for some simpler cases. Yeah. Here we do the same thing. Yeah. So let's work on a few simple cases to get idea for multiplication reduction. Okay, yeah. All right. So here we want to discover certain property from the experiments. If we do not do experiments, we do not have any idea how to do the reduction. Yeah. So we need to play around. So we need to work on our data a little bit to get some experience. All right, so let's do the experiment. It is easier to do experiments when the data sizes are small. Data sizes. So here, data size is the number of coefficients, or you can also treat the degree number, the polynomial degree number, as the data size. Yeah, so let's do our experiment work. The first one, let's consider n equals 2, degree 2 polynomial. Okay, yeah. So when we choose, so here, another question I want to emphasize a little bit here. So here, our first experiment example, we choose n equals 2. Yeah. Some of you may ask me this question: why you not choose simpler case, n equals 1? Right? N equals 1 simpler than n equals 2. Yeah. So the answer is, if we use n equals 1 for our first experiment, because it is too simple and it cannot provide us meaningful information. Yeah. Sometimes if the example is too simple, yeah, then it's hard to get helpful information. Yeah. So here we need to choose n equals 2. It is still simple, but we can get some meaningful information from the experiment. Yeah. That's the main difference. We choose 2 instead of 1. Yeah. All right, so let me show you how to get some meaningful information. Yeah. The current polynomial is a quadratic polynomial, degree 2, so we call it quadratic polynomial. Yeah. All right. Now, I ask you to make observation on this polynomial. We try to find some special property from this polynomial. Yeah. Now, I ask you to focus on the last two terms. Can you see some special property by looking at the last two terms? Any special property? Can you find? Yeah. Just look at the last two terms. Anything special property? What can you say? Say something. Some useful information. Yeah. You can factor an x out. Great. Andy. Yes. Spot on. Yeah. So you get a point. Yeah. You get a point, Andy. Yeah. Common factor property. So we call it common factor property. X is the common factor. Yeah. So that property is useful. Yeah. If we go back to n equals 1, you can see you cannot find common factor if we use n equals 1. All right? Yeah. A, because you only have a0 plus a1x. You cannot see any common factor. Yeah. But if we choose n equals 2 case, then we can see the common factor in the last two terms. Yeah. So that's the main difference. All right. So now we want to study, we want to explore this common factor property. All right. So here the critical property is common factor. So we want to take advantage of this common factor property to help us to do our goal, our target, multiplication reduction. Yeah. All right, so now let's do factorization. Okay. The factorization work, that's simple. Yeah. We just factor that x out. As Andy told us, yeah. After this factorization, now I ask you to count the number of multiplications before and after factorization. Before and after factorization. Let's count twice. The first time before the factorization, second time after the factorization. Okay? All right. Before factorization, the first term contains one multiplication. The second term contains two multiplications. 1 plus 2, we get 3 multiplications. Then, after factorization, can any of you do the counting? How many multiplications do we have after the factorization? Can you count quickly? How many? Exactly, 10. Yeah. 2 multiplications. Good. All right. The first one, 1 here, right? X times parenthesis. The second multiplication inside parenthesis, a2 times x. Total 2 multiplication. Can you see the reduction? From 3 to 2. Reduction. So that's the meaningful reduction, right? Although only 1 multiplication fewer, but definitely it is significant. It is meaningful, right? Yeah. So we can make our conclusion. Okay? So the conclusion, if we apply the factorization technique here, we get a multiplication reduction gain from 3 to 2 reduction. 3 to 2. Yeah. That's quite significant. That is just for a simple example. N equals 2. Yeah. Yeah. So that it's a very promising progress, right? Very promising progress. Okay. So this experiment encourages to work along this direction. Yeah. Yeah. So the summary, we change the order. Yeah, because after you do the factorization, you change the order to apply addition and multiplications, right? You change the order. It's the order you used is different from the orders you used without factorization, right? Yeah. So here, the summary, we change the order of operations by factorization that results in better efficiency. Results in a better efficiency number. All right. So let's keep going. Yeah. Let's keep going. Question: can we generalize this idea to the general N? Yeah. Our goal. Yeah, this is just our first experiment. Our goal, we want to get a result for the general N. Yeah. So let's continue our work. Yeah. All right. Because if we only used our experience from the first experiment, we feel still not quite enough. Yes. We get some valuable experience, but still not good enough to get a final conclusion for the general case N, right? Yeah. Because we need to have more experience before we feel comfortable to make our final conclusion. Yeah. So how to get more experience? Let's do another experiment. This time we work on N equals 3. Yeah. So we try, because this time we have experience from N equals 2, so we do the similar thing. We do the similar factorization thing. And hopefully we can do better. Yeah. Yeah. All right. So let's work on this cubic polynomial, degree 3. So we call it cubic polynomial. All right. Key to the success. We know from the previous experiment, the key to the success is factorization technique. The reason we can do the multiplication reduction because we take advantage of this factorization technique. All right. So our decision, we want to take advantage of the factorization technique. Yeah. All right. So let's try it. So we know this direction, but we need to fix the details here. Yeah. The factorization should cover as many terms as possible. Yeah. So, yeah. All right. So here we have total 4 terms, but when we look at the common factor, we have to ignore the first term. Yeah. If we include the A0 term, then we do not have common factor. Yeah. Just like what we did in the previous example, we ignore A0 term. Yeah. So here, the same thing. After we skip A0 term, we can factor the common factor X out. There, inside the parenthesis, there are 3 terms, 3 remaining terms inside the parenthesis. It's another quadratic formula. Can we do a little more on the quadratic polynomial inside the parenthesis? Can we do further factorization inside the quadratic polynomial, on the quadratic polynomial inside the parenthesis? Further factorization. Yes, the same as we did in the previous example. So let's do another round factorization. Inside parentheses, we can still do another round factorization by skipping the first term. By skipping the first A1 term, we can do another round factorization, right? Yeah. So let's do the factorization like this. Yeah. 2 rounds of factorization. So you can call it this time. We do 2 rounds of factorization. Right? Yeah. Now I ask you again, can you tell me what is the total number of multiplications we need after these 2 rounds of factorization? 3. Yes, very fast. Eldon gave us the answer 3. So 1 here, second one here, the third one here. The total 3. Total 3. Yeah. Now we want to compare. How much is the improvement? So here we have, so after factorization, our number of multiplication 3, but before the factorization, this term contributes 1 multiplication. This term contributes 2 multiplication. This term contributes 3 multiplication. So the total multiplication number 6. Now you can see the reduction is from 6 to 3. More reduction, right? Our previous experiment, only 1 difference, from 3 to 2. So the improvement is 1 multiplication fewer. Here, 3 multiplication fewer, right? Yeah. So we made better improvement when n equals 3. Here, so you can see, yeah, this direction works really well. Yeah. So we want to, continue along this direction to solve the whole problem. Yeah. So let me check the time. All right. Yeah. So let me pause a little bit. Let you take a break. At a